BRC is going to be talking about our epidemiological analysis with our whole genome SNP and core genome MLST services. So we're very glad to have you here for this. If you missed our last webinar, we gave a quick overview on the BVBRC, and if you're unfamiliar, we take publicly available data across the bacterial and viral space. We have 14 million genomes. We bring the data in with uniform annotations, query our metadata to make it more useful for you. You can programmatically and batch access that data, or on our website, use our analysis services. So we have over 30 analysis services that provide you publication-ready results. And when we get to the next slide, you'll get to see some of those examples, but those analysis services can be run on your private data, which will stay private to you, or on that public data we just talked about. We'll generate user-friendly reports and visualizations to really make that as useful for you as it can be. We have a robust user community with over 70,000 registered users that cite our resource often. We have guided classroom activities and live and virtual workshops like this webinar for you today. On the next slide, you'll see an overview of our analysis services. So this is what they look like on the BVBRC website, and Nicole is going to take you through that. And then those are some of those publication-ready figures that you can generate from BVBRC services. And if any of them stick out to you right now, or if you are wondering about how to use something that we're not talking about today, we're always here to help. And you can reach us at help@bvbrc.org, and I'll put that in the chat. But excited to have Nicole talk us through some of these new services.
Thanks, Anna. Hi, everyone. My name's Nicole. I'm one of the developers at the BVBRC. I'm really excited. We don't get to talk to people as much, so this is very exciting. We'll talk today about sequence typing at the BVBRC, and I'm giving an example of two services and how to use the genomes. But even if you're not as interested in these types of analyses, I hope that it gives an idea of what our services have to offer and even our platform. If you aren't a current BVBRC user, I hope that we can get your interest, and I hope you go to the website and poke around and see what we have to offer. But jumping into today's topic, we're talking about sequence typing. There's different ways of comparing genome isolates, and on our chart here, we have different levels of discriminatory power, beginning with traditional MLST. We say traditional because this is an older technique from when sequence coverage was covered less than it does today. It focused on housekeeping genes and identified which genes were in your isolate to give you an idea or a sequence type, a way to describe the genome, and that was standardized across labs. This is added to genomes as part of the annotation pipeline, so it's available in the metadata. In our genome page, which I'll show you today, we have core genome MLST, and this is one of our analysis services. We are looking into how to incorporate it into the annotation pipeline, but for now it's only available via service submission, and we'll walk through the submission page and outputs today. The concept behind core genome MLST is similar to the traditional MLST, but a much higher level of granularity. It covers all the genes, or at least the core genes, in a genome, and that can be around 1,000 to 3,000 genes depending on the pathogen. And again, this is used to determine a sequence type, a way to compare isolates at a glance. Then at the highest discriminatory power, we have single nucleotide polymorphisms, which is available through our whole genome SNP service. This covers the entire genome. Unlike the MLST methods, it covers genic and intergenic regions, the spaces between the genes, and this gives you information at the nucleotide level, which is really helpful when strains are nearly identical. So we'll walk through core genome MLST first. We use a publicly available tool called Chewbacca. The schema on the right is from their original publication. This top part is describing how they rely on what's called a schema to define the target loci or genes, describe the genes that should be in the genome for that species. And it's created by taking reference genomes and kind of stacking them together and understanding what genes are within that organism, where should they be. Then when you pass your genomes, it performs what's called allele calling to, similar to like a classification exercise, identify what genes you have. Right now, we're supporting 32 priority pathogens, and our schemas are curated by Rhydome. I created this as a toy example of how you can think about sequence type. So we have, this is again kind of simplified, but we have 3 example genomes that each have 3 genes. In the first position, they have the same exact sequence and same gene present. In our second, we see CCG, but then it goes to CGG and CGG. So here, genomes 2 and 3 have the same version, but genome 1 differs. And then our gene in the third position is the same across all 3 genomes. And while the schemas, as I mentioned, have like thousands of genes, I just wanted to have a visual illustration of the sequence type. So this would be called, and again, a fake name, sequence type 1. And while these two could be called sequence type 2 and sequence type 2, which gives you like a quick way, especially say it's an outbreak scenario, to compare 2 isolates, and especially if they're coming from different places, have an idea of what you're looking at. When you run the service, you get much more than just this information. You get an allelic profile, a core genome, neighbor joining trees, and an interactive report, which we'll walk through together. So now we're leaving MLST and discussing whole genome SNP. In this case, we use a tool called KSNP4. This tool operates by breaking your genome sequences into shorter sequences called kmer. The K stands for the length of the sequence piece, and that is actually determined by KSNP4. For viral genomes, it's a little shorter because of how the genomes operate, and bacterial genomes can be longer. And this allows the service to be reference-free, so we don't have the concept of a schema here, which can be great if you're trying to react quickly to something going on. And below is a snippet from one of the output files. We'll walk through it together, but the aim of this file is to describe the SNP, where is it in the sequence, and what genome can you find it in. So starting on the left, we have the position, and there were more rows. I selected these to keep it simple. At position 10, this was our kmer sequence. In this case, the kmer sequence was 20, which means we have, well, maybe 21 because we have 10 and 10 nucleotides. And the period represents where the SNP was. In the SNP column, we have most of the 4, or all 4 of the 5 have the G nucleotide, but in our third genome, it was changed for an A. Then on the right, we have the genome ID. This is used across the BRC to ID that genome. So you could take this from the report and search it, which I'll show you once we're on the website portion. The output of this service is phylogenetic trees. There are many, many files for downstream analysis, especially if you're more interested in studying phylogeny. There's a lot of information in the output files, so don't ignore that. And then a comprehensive interactive report. And to demonstrate these services, I've prepared an outbreak example using Shingha toxin-producing Escherichia coli from serotype O104H4. This outbreak occurred in late spring of 2011, impacting thousands of people stemming from raw sprouts. So I'll switch to our website. Okay, does this window look okay for everyone?
Yep,
Okay. So this is the Escherichia landing genome page. We have a large number of genomes. I'll highlight a few things. You could click on any of the taxa and go up in taxa level. how I got here was by clicking on Escherichia here in the list. But I just want to mention, and we'll remind you a lot in our materials, that we have more bacteria and viruses than what's listed here. So don't look here and then say, oh, never mind. We have a really comprehensive list. So go be sure to check everything out. Then each of these pages, our data pages are really congruent. So if you're more into proteins, which we have it labeled as features for the most part, like right here, it follows the same
So thank you all for joining us for our second Tools for Tomorrow webinar series meeting. This is a monthly webinar across the NIAID BRCs. So we have the BVBRC this month. Next month, we will hear from BRC Analytics on analysis of key C. aureus datasets. So feel free to check in next month for that.